Bismillahirrahmanirrahim. So last time we discussed Cartesian vectors in two dimensions, or what we also called coplanar vectors, so that all the vectors lie in a plane. So the obvious extension of this concept is vectors in three dimensions, so where our vector can point in any direction in three-dimensional space. Okay. So the obvious extension from last time is that first we were looking at the I hat component and the j hat component, and they formed a plane, and we were completely working in that plane. But now we add a third component, which is called the k hat component. So now our vector can lie anywhere in this place, in this space. Okay. So now we write our vector A as, this is a vector because this is written in bold, is equal to a vector in x direction plus a vector in y direction plus a vector in z direction. All of these three are also vectors, they are not numbers. So if we were to represent them as numbers, we would say that, so vector A is equal to ax I hat. Now this ax is just a number, plus ay j hat plus az k hat. Okay, let me just make that a bit more clear. Okay. So now we are representing our vector as a sum of three perpendicular vectors, unlike last time where we were representing our vector as a sum of two perpendicular vectors. Okay, so last time we only had I hat component and j hat component, but now we have an I hat component, a j hat component, and a k hat component. Okay. So now our Cartesian vector representation, as I have written already here, is vector A is equal to ax I hat plus ay j hat and plus az k hat. So we have three unit vectors rather than two from last time. Okay. So how does that change our concepts? So the next important concept is the magnitude of a Cartesian vector. So just by natural extension, previously the magnitude of the vector A was just given as the square root of ax squared plus ay squared, but now because we have three components, the magnitude of A is equal to the square root of ax squared plus ay squared plus az squared. We can just think of it like applying Pythagorean theorem twice. So first of all, we can apply Pythagorean theorem on this triangle. So a prime is just equal to ax squared plus ay squared square root. So let me write it for you. So first of all, so we want to find the length of this line A, which is the magnitude of this vector A. So to find this length, first of all we find this length, which is a prime, and a prime is given as ax squared plus ay squared and square root of the whole thing. Okay, so this is just a prime, and now we want to find A, and so from this, if we look at this blue triangle, we see that A is nothing but a prime squared plus az squared. So we say that A is equal to the square root of a prime squared plus a z squared. And if we plug in the value of a prime as square root of ax squared plus ay squared, it is easy to see that we get this result. Okay, So we just apply Pythagoras theorem twice and we get this formula for magnitude of a three-dimensional vector. Okay, so moving on, and so now the tricky question is, how do we determine the direction of this vector? Previously in 2 dimensions, if we were to give the angle from one of the axes, that would completely classify the direction of that vector. But now, because we have this vector in 3 dimensions, we can measure the angles from 3 different axes. So we can measure an angle from the x-axis, we can measure the angle from the y-axis, and we can measure the angle from the z-axis. And so these are what they are called the alpha, beta and gamma angles. So alpha is the angle between the vector A and the positive A axis, and beta is the angle between A and the positive Y axis, and gamma is the angle between A and the positive Z axis. Okay, so one thing to note here is that these angles do not lie in these planes. So this angle alpha does not lie in AZ-AX plane or in general. So AY and angle beta does not lie in AZ-AY plane. It is out of the plane, all of these 3 angles. Okay, so these relationships are pretty obvious. We just need to use some trigonometry. So let me just show you how we get this first one, and then the next 2 follow up pretty straightforward from there. So to understand how we get this cos of alpha is equal to AX over A, we have to look at this tilted triangle, which is something like this. This is the third side of the triangle. Okay, and this is again 90 degrees. Okay, if we were to look at this angle, this triangle, which does not lie in any of these usual planes, it is out of the plane. Okay, so maybe it's better that I draw this line with a color which is not confusing with any of the other colors on the screen. So we draw this vector. Okay, this triangle. So this triangle which connects the origin AX, I hat and A, these 3 components. So this is the triangle. So now this is the angle, and this is 90 degrees. So this angle is 90 degrees. Okay, so it's not very obvious to see why this angle would be 90 degrees, but imagine that you are looking at this triangle from here. So you look at this triangle from this side, so you would see actually a right angle triangle, and this angle would be 90 degrees. Okay, so now we apply the simple trigonometric identities on this triangle. We know that cos of an angle is equal to base over hypotenuse. Okay, base over hypotenuse. Okay, so now this is the base, this side is the perpendicular, and this side is the hypotenuse. Okay, so now when we do cos of alpha, so we would say that cos of alpha is equal to base over hypotenuse, and base is nothing but AX, and the hypotenuse is nothing but the magnitude, which is A. Nothing, no subscript. Okay, so I hope this is clear. Similarly, we get cos of beta is equal to AY over A, and cos of gamma is equal to AZ over G. Make sense? So let's move on. These 3 angles have to satisfy this identity, that cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. So it's pretty obvious from the first 2. So we can say that this equation, let's name it number 3, and this is number 2, and this is number 1. So 3 follows from 1 and 2. Okay, how does it follow? We just plug in the values. Okay, so we know that cos of alpha is equal to ax over a. When we say cos squared of alpha, we get ax squared over a squared plus ay squared over a squared plus az squared over a squared. But we already know that ax squared plus ay squared plus az squared is equal to a squared. So they cancel out and we get 1. So what does this tell us about these angles? That they are not all independent angles. Okay, so if we know alpha and beta, we can always find gamma up to a negative sign. Okay, so if we know alpha and beta, so gamma can either be this angle or it could be in the other direction, in the negative z direction. Okay, so we can say that only 2 of these variables, only 2 of these angles are independent. The third one is constrained by the fact that they have to satisfy this identity. Okay, this is similar case as we did in 2 dimensions. Let me just remind you guys that in 2 dimensions we had something like, so if this was angle theta and this is x and y, and let's just call this angle as phi, so we know that phi is nothing but 90 degrees minus theta. So when we know the angle from the x axis, that already completely classifies the angle from the y axis. So there was only one independent variable. Okay, but now in terms of direction we have 2 independent angles. If we know any of these 2 angles, maybe we know beta and gamma, so we can calculate or find alpha. Similarly, if we know alpha and beta, we can find gamma. So I hope this point is clear. So the other important concept is what we call a unit vector. A unit vector is just a vector pointing in the, a unit vector of a vector A is a vector which is pointing in the direction of A, but it has a magnitude of 1. Okay, so a unit vector is a very common concept which is used to express the direction of a vector. Okay, so by definition, the unit vector of a vector A is just the vector A divided by its magnitude. Okay, so if we were to write it in the other notation with the arrow notation, so we would say that the unit vector of A is equal to vector A divided by the magnitude of A. So just by the construction of a unit vector, we can already see that the magnitude of a unit vector is just equal to the, because this is just a scalar number, so this would just be equal to the magnitude of A divided by the magnitude of A, which just means that this is equal to 1. So by definition, unit vectors have a magnitude equal to 1. So unit vectors are very commonly used to specify the direction of a vector. So if we were to write a unit vector, so we get ax over a I hat plus ay over a j hat plus az over a k hat. But we already knew that ax over a is nothing but cos of alpha, ay over a is nothing but cos of beta, and az over a is nothing but cos of gamma. So we can just say that the unit vector in the direction of A is equal to cos of alpha I hat plus cos of beta j hat plus cos of gamma k hat. So now this again another way to write a unit vector is equal to its magnitude times the unit vector. Okay, so this method of writing a vector, so this is the magnitude and this is the direction. And direction is given by all of these three angles. So these are just, all of these are equivalent representations of the same vector. We can write a vector as its x hat component, y hat component and z hat component, or we can write that vector as a magnitude and a unit vector which specifies its direction, or we can write a vector as a magnitude and all of these three angles. Okay, so all of these are equivalent representations. Okay, so one thing to note here, by if we look at a unit vector graphically, let's assume we have a vector A which is just 2.5 a hat. So it's a vector pointing in this direction and has a magnitude of 2.5. So the unit vector is going to have the same direction. This black is the unit vector and blue is the actual vector. So A is going to have the same direction as vector A hat is going to have the same direction as A, but it is going to have a unit length. Okay, so moving on. So these another representation of measuring the angles in 3 dimensions is what we call transverse and azimuthal angles. Okay, so previously we were measuring 3 angles, alpha, beta and gamma, and we already said that we only need 2 angles rather than 3, and the third is completely determined by 2 of these angles. Okay, so now we use another method to determine the direction of a 3-dimensional vector, and both of these methods are very commonly used, and we would be using both of them in our problems, and in real life I would say that transverse and azimuthal angles are more common than alpha, beta and gamma. So what are transverse and azimuthal angles? So let's assume we have a vector A. So first of all we measure its angle from the z axis and we call it phi. So notice that this phi is the same angle that we were previously calling gamma. So we can say that angle phi is the same as angle gamma. So this was the angle we were measuring previously, and both of these are the same angles, exactly the same, and they actually have the same form also. So cos of phi is equal to az over a, which is the same as same formula we had for gamma. But the second angle, how do we measure the second angle? First of all, we take the projection of this vector A over this plane. So what do we mean by a projection? So let's assume that we have a very big torchlight up here. So this is sending in light. So my torchlight is not very good. So any vector in 3 dimensions would have a shade on xy plane. Okay, the image of this vector on the xy plane, and we call this a projection of this vector over the xy plane. So let me just write it for you guys. So A prime is the projection of A on x plane. Okay. So now once we have this projection A prime, we measure the angle of the projection from the x-axis and we call it theta. So now we represent the direction of this three-dimensional vector using two angles. One is phi, which is just the angle from the z-axis, and the other is theta, which is the angle the projection of that vector makes from the x-axis. Okay. So it is easy to understand that why we get this formula. Like previously we had cos of gamma is just equal to az over a, but now we know that gamma is equal to theta, so we can just say that cos of theta is equal to az over a, and which is exactly what we got here. Okay. The other how do we represent ax and ay in terms of a? So first of all we can see that ax is nothing but a prime cos of theta and ay is nothing but a prime sine of theta. So now we are looking at this darker angle. So if we look at this dark blue triangle, we can see using this angle is 90 degrees. So we can see that ax is equal to a prime cos of theta. This is what we have here. But we already know that a prime is nothing but a sine of theta. So this is also equal to a prime. So this length is also equal to a prime. So a prime is just a times sine of phi. So we get ax is equal to a sine of phi cos of theta, and ay is nothing but a sine of phi sine of theta. So now we reconcile all of these three and we get that vector A is equal to a, this is ax, a sine of phi cos of theta I hat plus a sine of phi sine of theta a j hat plus a cos of phi k hat. So just to reiterate, this is nothing but ax and this whole thing is nothing but ay and this is nothing but a c. Okay, so I really mean I don't include the, so it's till this point. Okay, so I hope it is clear. So this these angles are very popular in general engineering, and they have another name which is, they are more commonly known as spherical coordinates. Okay, so we would learn them in more detail later on, but just a shout out that these angles are also form a coordinate system, and so that is called spherical coordinate system. Okay, maybe you might have already learned it in your college, so I didn't know about it. So now we want to add vectors in 3 dimensions. So all the results follow exactly like we did in 2 dimensions, but now first of all the direction can either be given as alpha, beta and gamma angles, or it could be given as transverse and azimuthal angles, and the magnitude is just equal to ax squared plus ay squared plus az squared square root. Okay, so now we would solve some problems to understand the concepts more clearly. Okay, so the problem says express the force F shown in figure 2-30a as a Cartesian vector. Okay, so this vector F is a force which is 100 pounds. So again we discussed in our first chapter that in this book sometimes we would be using pounds as the unit of force. So we don't have to be panicked about it. It's just another unit for force. Okay, and we want to write F into its x into its Cartesian vector form, which means I want to write F. So let me just start off by saying that the question wants us to write F as Fx I hat plus Fy j hat plus Fz k hat. Okay, so there are these connecting lines, I should get rid of them. Okay, so this is the Cartesian vector form. This is the Cartesian vector form. Okay, so now we just need to determine the value of Fx, Fy and Fz. So first of all, let me just say that this angle, so the angle from the xy plane is 60 degrees, which means this angle is going to be equal to 30 degrees. Okay, and this is equal to theta. So now that we know the value of theta, we can simply say that Fz is nothing but 100 pounds times cos of 30 degrees. Okay, and cosine of 30 degrees is equal to 0.866, so we get 86.6 something. So this is approximate. So maybe you guys would have a calculator. So this is completely correct, this might be wrong, so you are warned. Okay, so next we want to find Fx and Fy. So I know that so first of all, just by looking at the drawing, we know that Fy is going to be in the negative direction. Okay, so first of all, let's just say that this is F prime. Okay, the length of this vector is F prime, like we discussed previously. So F prime is going to be equal to 100 pound times sine of 30 degrees. Sine of 30 is a half, which means that this is just equal to 50 pounds. Okay, so now we have F prime, we can just find Fx and Fy. Okay, using this angle theta. Okay, sorry, so this angle according to the definition was, this angle was equal to phi, the other angle was equal to theta. Let me just correct that for you. Okay, so now Fx is just equal to 50 pounds times cos of 45, and Fy is just equal to minus 50 pounds sine of 45. Okay, so why do we get this minus sign? Because just from the looking at the diagram, I can see that the y component has to be negative. Z component is positive, x component is positive, but the y component has to be in the negative direction. So that is why I just put up a negative sign up front. Note that we can also say that theta is negative. So we could equally say that theta equals minus 45 degrees. Okay, but so you can do, if you were to put theta equals minus 45 degrees, then you do not need to put this extra negative sign, because sine of minus 45 is minus sine of 45. So the sine and cosine would already adjust all the signs up front. Okay, but you can also say that I already know that Fy is going to be in the negative direction, so I can just put up the negative sign up front and take sine of just 45 degrees. Okay, okay, so 45 degrees is 0.707, so 50 times 0.707 is just something like 35 point something, whatever. Okay, and similarly here. Okay, so now I can just plug in the value of fx, fy and fz in this equation, and we get the Cartesian vector form for force F. Okay, and we already see that this is the same result that we get, 86.6 k hat minus 35.4 j hat plus 35.4 I hat, and this is exactly what we found using this method. Okay, so now we look at the second example for Cartesian vectors in 3 dimensions. So we have a force F which has a magnitude of 80 pounds and acts within the octant shown. Determine the magnitudes of the x, y and z components of F. So there is a force which is acting along this direction as shown in the diagram, and so this is a new word for us, octant. So like in 2 dimensions, our axis, our whole space is divided into quadrants. So let me just draw it. So in 2D, we know that for 2D my whole space can be divided into 4 quadrants. So this is my first quadrant, this is my second quadrant. So, okay, so this was supposed to be a second or third. So this is my second quadrant, and this is my third quadrant, and this is my fourth quadrant. Okay, but when we are dealing with 3 dimensions, our axes divide the whole space into not 3 but 8 octants. So octant is just the 8th path, where a quadrant is just the 4th path. So the first octant is this one, which has all x, y, z positive. So maybe this is x, this is y, and so to keep it, this would have to be z. Okay, so this is my first octant. Down below, this would be my second octant, third, fourth, fifth. So in 3 dimensions, all of space is divided into 8 octants. So here it just means that in this octant, x, y and z, all 3 are positive. Okay. So we want to find the magnitude of x, y, z components of F. So basically we want to find fx, fy and fz. Okay, so to find fx, we are given alpha and beta, and we are not given gamma. Gamma is the third angle. So first of all, we know that we have the identity that cos of alpha squared plus cos of beta squared plus cos of gamma squared equals to 1. What does that mean for us? Well, basically it means that even if we are given 2 of these angles, we can find the third one. So in this case, cos of gamma squared is nothing but 1 minus cos of 60 squared minus cos of 45 squared. And of course it is obvious that this squared is the squared of the cosine, not the squared of an angle. It wouldn't make sense to take the cosine of a square of an angle, cosine of an angle, but the whole squared. So we know that cos of 60 is a half. This is 1 minus, so cosine of 60 is a half, and then you have to square the whole thing, and then cosine of 45 is 1 over square root of 2, and you have to square the whole thing. Okay, and so this is cos squared gamma. So from this equation we can find gamma as to be equal to, so this is 1 minus 1 by 4 minus 1 by 2, so this turns out to be 1 by 4. So cos of gamma is nothing but the square root of this, which means that this is equal to 1 over 2. So this implies that gamma equals, so again 60 degrees. Okay. So now that we have found the gamma angle, we can easily find fx, fy and fz. So using this let me just, I just erase this. So we remember the fact that gamma is equal to 60 degrees. That's it. So I know that f of x is just f times cos of alpha, and so this is equal to, f is just 80 pounds, and cos of alpha is nothing but cos of 60, which is a half. So we know that fx is just 40 pounds. Similarly, fy is nothing but f cos of beta, which turns out to be 80 pounds times 1 over square root of 2. Similarly, fz is equal to f cos of gamma, and so this is equal to 80. Again, gamma was also 60 degrees, so this is 1 over 2. So this is equal to 40 pounds. So I hope this makes sense. So we are only asked to determine the magnitudes of the x, y and z components. So this is the fx component, and this is the fy component, and this is the fc component. Okay, so let's look at another example. So now we are given, so both of these problems correspond to the same diagram. So we will look at both of these examples. So this is part of this example is from the book 2-78. So the two forces F1 and F2 acting at A have a resultant force of minus 100 pounds in k hat direction. So the resultant force is with a minus sign, means that the resultant force is downward acting. Determine the magnitude and coordinate direction angles of F2. So we are given F1, we are given the angles of F1 also, but we are asked to determine the angles of F2. Okay, so a few important points to make here. We are given the resultant to be equal to minus 100k. Okay, so let's just start it off. So because f of r is given to be 100k, so I know that f1 plus f2 is going to be equal to minus 100k. Okay, so I'm not going to write pounds in all of, because we know that all of these are in pounds, so we don't need to worry about that. We'll write the symbol just at the end. Okay, the units just at the end. So first of all, we can write down what f1 is. Okay, so f1 is a vector, so we can clearly see that f1 is going to have a negative z component, a negative y component, a negative x component, and a positive y component. Okay, so and so let me just draw a few things here. Okay, so this angle from its projection on the xy plane is 50 degrees, which simply means that this angle is going to be 40 degrees. Okay, so this is the angle that this force vector makes with the z axis. So I know that f1z is equal to, so it is f1, which is just the magnitude of, which is 60 pounds, times cosine of 40 degrees. Okay, so this is the z component, and so for x and y components we know that and this has to be negative direction, so we put a negative sign here. So f1x is going to be equal to f1 sine of 40 degrees. So this is a sine of 40 degrees because we want to find the projection, and then this angle is 30 degrees, and this angle is with the negative x axis, so we can say cos of 30, but then we have to put a negative sign also because fx is also in the negative direction, f1x is also in the negative direction. The third one is f1y, which is simply equal to f sine of 40 degrees, and then we have to do a sine of 30 degrees, but this is going to be in the positive direction. Okay, and so this is all f1. Okay, so these three equations, they all correspond to f1. Okay, so this is f1x, f1y, f1z. Okay, so now we know that the resultant is only in the k hat direction. Okay, so it has no component in the x direction, it has no component in the y direction. Okay, so we know for fact that f1x plus f2x has to be equal to 0. Why is that? Because there is no x component of the resultant of these two forces. So the x components of these two forces should add up to 0, which means that f1x, f2x, which is what we are trying to find, is nothing but f1 sine of 40 cos of 30. Okay, similarly we can say that f2y so this is I can just write that this is equal to minus f2 f1y. Okay, so this is f1y, we put a negative sign with it and we get f2y. So the last component is f2z. We know that f2z plus f1z is equal to minus 100, because we had a minus 100 k hat. So we can say that f2z is equal to minus 100 minus f1z, where f1z is given by this. Okay, so now that we have found f2z, f2x and f2y, we can write f2, and we want to find and determine the magnitude. So magnitude is just f2x squared plus f2y squared plus f2z squared. This is pretty simple. And then the direction angles, we can just use these cosine rules to find the direction angles. Okay, so I hope I don't have to find the magnitude for you guys. Let me just erase everything here and just write. So for magnitude of f2, this is just f2x plus f2y plus f2z, and you have to square all of them, and then you have to take the square root. Okay, so this is f2, this is the magnitude. So the second thing, we want to find the direction angle. So already first of all we can find the angle with respect to z axis, and this is the angle that we call phi 2 maybe is a better terminology, is just the cos inverse of f2z divided by f2. Okay, so from here we can find the angle phi, and similarly we can find theta. It's not very difficult. Okay, so I hope this part is clear. So the second, determine the coordinate direction angles of the force F1 and indicate them on the figure. So here we want to find the coordinate direction angles, which means we want to find alpha, beta and gamma. So let me just draw them on the figure. So alpha is going to be this angle, this is alpha, this is going to be beta, and this angle is equal to gamma. So we can determine them using the formulas for alpha, beta and gamma, which are given in the previous slides. Okay, so I hope these examples are pretty clear. So we would start the position vectors in the next video lecture. I hope everything is clear at this point. One thing that it is very essential for learning basic engineering mechanics is that you should practice many problems on your own, because there are many problems given in this book and there are many other textbooks given. The more problems you solve, the more comfortable you get with looking at different arrangements of vectors, and you can visualize the angles better with practice. Okay, so I hope this is clear.